Okay, so hey guys, it's Quinston, and today we are going to find an algorithm or method in order to find the maximum flow of data in a network basically. So how does this work? So we have this graph over here, and we are going to find the maximum amount of data which we can pass through this entire graph. What is the maximum flow? The technical term is what is the maximum flow of data or units through the entire graph. So this algorithm is called, or the method is called, the Fulkerson algorithm. I think it's Fulkerson's algorithm. And the way this works is, first you create the adjacency matrix, and then you calculate the minimum amount of flow, and you find, and then traverse the graph with a BFS, and then you find the minimum amount of flow which you can take out of the BFS, and then you do the steps over and over again. So in this part we are going to actually solve this entire graph, and then in the next part we are going to see how the code actually works. So yeah, let's first create the adjacency matrix for this entire graph. So how do you do that? Sorry. So this is the adjacency matrix. I'm going to start with a 0, 1, 2, 3, 4, and a 5. Then you have 0, 1, 2, 3, 4, 5. An adjacency matrix is basically a matrix which converts this graph into a matrix. I mean, we are just representing this graph in a different form. So if you want to populate this, you basically check which edges are where. So that there's an edge from 0 to 1. So I'm going to put a 16 over here. There's an edge from 0 to 2. So I'm going to put a 13 over there. There's an edge from 1 to 3. So I'm going to put a 12 over there. There's an edge from 1 to 2. So I'm going to put a 10 over there. There's an edge from, I think there's an edge from 2 to 1. That's going to be a 4. And 2 to 4, which is going to be a 14. There's an edge from 3 to 2, which is 9. 3 to 2, which is 9. There's an edge from 3 to 5, which is 20. 3 to 5 is 20. And there's an edge from 4 to 3, which is 7, over here. There's an edge from 4 to 5, which is a 4. And so how many are there? 14, yes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So everything else, just imagine it to be 0. So yeah, I'm considering this to be a U and this to be a V, just because I want to have kind of a good thing over there. So what is the next step in this process? So in order to find out the flow, we first need to BFS this entire graph. BFS meaning breadth first search. Now, if you don't know what a breadth first search is, you should probably go and check out one of my videos in which I teach what a breadth first search is. In a breadth first search, we use a queue to actually traverse the entire graph. So that's what I'm going to make over here. So this is going to be our queue, and this is a queue, Q, U, E, U, E. And we also need to have a few more things. We need to have a parent array. Now let me just draw this properly. And we also need to have a visited array. So this is going to be a parent array, and this is going to be a visited array. And I'm going to have indices 0, 1, 2, 3, 4, and then 5 is not. 1 second. 0, 1, 2, 3, 4, and 5. So the parent array will basically store the parent of a particular node, and the visited array will basically keep track of which elements are already visited. So how do you start this process? So the first thing is we check the first node. We start with the first node basically. So the first node is 0. So you queue it up. You queue the first node, and then you say that the first node is visited. It's visited. It's visited. And also that the parent of the first node, there's no parent for the first node. So basically in the parent, you put -1. The next step is pretty obvious. You dequeue the element and you check what possible paths are available next. So the possible paths are 1, because there's an arrow from 0 to 1, as you can see, and there is a 2 arrow from here to here, the same thing. So 1 and 2 are possible. So you queue 1 and 2. I queue 1 and 2. Next, I basically check the same thing. Now 1 and 2 are visited, so I basically put T and T over here, and also they know what their parent is. Their parents are 0, right? 0 is the parent for both 2 and 1 because we just saw Y. The next step is to dequeue 1 because in the queue you follow the rule first in, first out. So 1 came before 2, that's why 1 will be dequeued first. You do the same. What are the possible paths for 1 to take? So there's an arrow from 1 to 3 and there's an arrow from 1 to 2. But 2 is already visited, so you can't really do it twice. See, 2 is already visited, so you can't do it twice. That's why you only have to put in 3. So I put in 3, I say that 3 is visited, and I know the parent of 3. The parent of 3 is 1. Next, you dequeue 2, and you basically do the same thing over here. What can 2 do? 2 can go to 1 and 2 can go to 4, but 1 is already visited, so only 4. So 4, and then T over here, and then the parent of 4 is 2. Now we dequeue 3. Now if you dequeue 3, where can 3 go? 3 can go to 2 and 3 can go to 5, but 2 is already visited, so only 5. So put 5 over here. So this is T, and then 3 can go to 5. So basically you have 3 over here. So then if you dequeue 4, you basically find that this is also visited and this is also visited, so there's no possible entry. Then you dequeue 5, you find that 5 cannot go anywhere, so it doesn't matter. So this is the parent, and this is our visitor array. So using the parent array, we are going to track out a path in this entire graph. So what is the path we found? We found that the path ends at 5, right? The path ends at 5. But there is a path from 5 to 3. So this is one path. Then from 3, there's a path to 1, right? Because 3 is over here, 5 to 3, 3 to 1, 3 to 1. Then there's a path from 1 to 0. So this is the first path which we found. So how do we do this? We started with 5, 5 goes to 3, 3 goes to 1, and 1 goes to 0. The next step is remove the maximum amount which you can from this particular path. Now what is the maximum we can remove? We can remove the maximum of 12 because there's a 12 over here, there's a 12 over here. So if you remove a 12, you basically subtract 12, you get a 4 on this edge. You get a 0 on this edge, and you get an 8 on this edge. So basically that's what you get. So you keep this as a back, so you have to keep this. This is your path flow. So this will be added up and that will form your maximum flow. Okay, let's select a different color now. I'm going to select a green, and we'll have to do this entire step over again for a different value now. So what we're going to do is we're going to do this entire step but with the new graph which we got. So what is the new graph? The new graph has 0 to 1, which is 4. So this is eliminated, and we got a 4 over here, right? Then we have a 12 which was removed, and we have a 4 in its place. Oh, sorry, a 0 in its place. A 0 in its place. And then we have a 20 which was removed, and what do we have in its place? We have a 8 in its place. So now we are going to do this entire step over again with these elements. So how do we start? We start with 0. So you put 0 in the queue, you say that 0 is visited, and the parent of 0 is 1. Then what you do is you pop off or dequeue 0, you check where it can go. It can go to 1 and 2, then 1 and 2 are visited, and the parent of 1 and 2 is 0 and 0. Next you check, you dequeue 1, where can 1 go? 1 was able to go to 3, but now the path to 3 is 0, so 1 cannot go to 3 anymore, but 1 can go to 2, but hey, 2 is already visited, so that also is not possible, so 1 cannot do anything anymore. So this step is skipped for 1. dequeue 2, 2 can go to 1, but 1 is visited, 2 can go to 4, so yeah, I didn't do the green marks over here, yeah. So 2 can go to 4 now, so you put in 4, but 2 cannot go to 3, so remember that, 2 cannot go to 3. So you put in 4, 4 is visited, and the parent of 4 is 2. Now you're at 4, you dequeue 4, 4 can go to 3 and 4 can go to 5. So 4 can go to 3 and 4 can go to 5. So you have t over here and t over here. The parent of both of them will be 4 and 4. So you start from 5 again. You start from 5 again. What is 5 going to? 5 is going to 4. See, 5 is going to 4. Then 4 is going to 2. See, 4 is going to 2, and then 2 is going to 0. 2 is going to 0. So this is the new path which you just found. So this path, you want to find the maximum amount you can take out. So you can take out a 4 over here. So you can add a 4. Take out a 4, this becomes 0 because you subtract 4. Then you take out a 4 over here, this becomes 10. Take out a 4 over here, this becomes 9. So basically you got this over here. This is the next path. Now we need to find one more path. So what is the next path we found? Let's see. I gotta delete all this, so I'll just delete everything. Again, with the same thing again and again. In the code it's much easier because you'll have to write this only once. Here it's a bit difficult. So you have to replace 13 by 9. Replace this by a 9. Then you have a 14. You replace 14 by a 9. Oh, sorry, a 10. Then you have a 4 which you replace with a 0. Okay. So this is your new graph which you just formed, and now we have to do the same process over and over again. So you have a 0. You start with a 0. Oh, sorry, that's a very bad 0. You start with a 0. You basically check which elements can go in. Now this is true and this is -1 because parent is -1 and 3 is 2. Then you check, then you DQ this, and you check where can it go. It can go to 1, it can go to 2. So you put 1 and 2 over here. You DQ 1. Oh, sorry, this I didn't finish this. 0 and 0. So you DQ 1, but 1 cannot go anywhere because there's a 0 over here and it's already visited, as you see. So forget about 1. You DQ 2. Where can 2 go? 2 can go to 4. 2 can only go to 4. 2 can't go anywhere else. So 2 can only go to 4. This is t, and the parent is 2. Because there's already left 10, right? There's already some amount of flow left in this. Then you DQ 4, and where can 4 go? 4 can go to 3, but 4 cannot go to 5 because this is now 0. So 4 can go to 3 now. So if you put a t over here, and 4 can go to 3, this is a 3. The parent of 3 is now 4, and then from here, if you put 3 in there, you can DQ 3, and 3 can now go to 5. Yeah, 3 can definitely go to 5. T and 3. So then if you DQ 5, there's nothing else because 5 doesn't point to anything. So how does this path form? You go from 5 to 3, 5 to 3. This is one path. Then you go from 3 to 4, 3 to 4. Then you go from 4 to 2. See, 4 to 2, 4 to 2. And then you go from 2 to 0. So this is your next path which you just formed. Okay. So what is the minimum amount which you can take out of this? I think it's 7, right? 7 is the minimum amount. So there's 9 over here, there's 10 over here, there's 7, and there's 8. So 7 is the minimum amount. So you can add that over here. So you can take out 7. If you take out 7, this will be a 2. This will be a 3. This edge will be 3. This will be a 0. And this will be a 1. Now as you can see, this edge, and this edge all are 0. So even if you run this step over again, it won't work because it won't ever reach the sink, and we can only calculate the path if we have a path to the sink. So basically you are done, and that's it. So if you add this up, you get 12 plus 4, which is 16, 16 plus 7, which is 23. So maximum flow in this graph is 23, and yeah, this is how you basically formulate it. And in this next video, I'm going to show you what the basic, how the code basically works for this entire thing. So thanks for watching, guys. I'll see you in the next video. Okay, so now let's look at the code. Now, as we saw, the graph which we checked was 6 nodes, right? So I have this n over here defined to be a 6. I'm going to change the color. I'm going to use something pink. Okay. Now this is a 6 over here, right? Because our nodes are 6. I have this array which I defined, and I called it parent tracker because it's going to keep track of all the parents of each node. I also declared something called infinite. It's going to be the maximum element of checker. So check for the maximum elements. And yeah, let's start with the main function initially. So this is the graph. Now this is the same graph which I have over here. So nothing different. It's the same graph. It's the same adjacency matrix which we created over here, and it's the same. It's not different. Now this is a line which I did to append about 6 elements to the parent tracker. All of them are 0, so you don't have to worry about that. So parent tracker would append 0. So basically populate the parent tracker with about 6 elements because I want to use them later. Next, I'm going to call this print function, but along with that I'm going to say that the maximum possible flow is this. Then I'm going to replace this value with the formatter, and then we're going to call the forward Fulkerson algorithm function, pass into it a graph, pass into it the 0, which is the sink, the source, not the sink. This is the source and this is the sink, because n is equal to 5 but n minus 1, n is equal to 6 but n minus 1 is 5, so that's what we're going to pass in. Let's go to what this algorithm, this function actually does. Let's see. So this function, it defines u and v. So u and v are going to be our pointers to each of the elements in the graph, the nodes of the graph. So very important. We define both of them as to be 0. Now we declared something called the residual graph. I don't want to make changes in the original graph, so we declared something called as the residual graph, and that would be what we'll be making changes to. Then you have something called the max flow. The max flow will keep track of everything. Okay, it will keep track of everything. This is basically what the max flow will keep track of, the 12 plus 4 plus 7. Okay, so while the breadth first search, so we basically call this function the breadth first search function, and this will return either a true or a false, and depending on that you will execute the next part. So let's check out what the breadth first search does. Now if you already know what the breadth first search is, you probably don't have to check this out, but for others I'll have to go and see what's happening here. So the usual stuff, you define a queue, you define the visited array, you already have the parent array up there, you append the source to the queue, you set the visitor to true for the source, that is 0. Source here is 0 currently, and then you basically say that parent tracker source is equal to -1. We saw everything over here. All of this is the same thing. It's just in the form of code. So next we have while not len q equal to 0. So while the q is greater than 0. So while q is not 0, that's what this means. So you pop off the q, you basically pop out the first element because the q first in first out, right? So yeah, you give that to u. So basically I'm checking out u, this part over here. Then what I'm doing is I'm saying that for v in range of 0 to n, for all the other nodes, if there exists a path between u and v, and that v is not visited, and that the residual graph is greater than 0. All these we saw before, right? If there is a path, and if it is not visited, and if this value is greater than 0. See, we have done this before. It's just that now we're doing it with u and v. So if you find any which satisfy these conditions, add them to the queue, queue.append, add them to the queue, make the visited areas true, and put that parent value in there. So the parent value which we just put over here, the same thing. For v, the parent value will be u, because it's going from u to v. It's going from u to v. That's what we're doing over here. Remember that. Now this will run in a loop, and it will give the same things that we did over here. You pop it, you put it back. Pop it, visited true. Pop it, do the same thing over and over again, and that's what happens. Okay? Then you check if the sink was visited. As I said, you always want to have the sink to be visited. You can never have the sink not visited. That's why when everything became 0 over here, you couldn't really go back to the sink. And that's why we basically ended the thing, right? So if the visited of sink is not true, then you return false. Else if you have visited the sink, then you return true. And if you return true, only then this while loop will run. Okay? So initially to path flow, so if this while loop runs, it means that the parent tracker has the necessary tracking parameters which you need in order to create the path back. So you create a variable called path flow, you name it as infinite, then you say that v equal to sink. So v is the end and u is the beginning, always remember that. So v is a sink. While v is not the source, while v is not equal to 0, u equal to parent tracker of v. So what is the parent tracker of v? Parent tracker of v, the sink, is this u. So this becomes our u right now. So if this is u, then what is the max flow between the path flow and the residual graph? Now infinite, the path flow is equal to infinite, right? The path flow is equal to infinite, which is a very big number. The residual graph of uv, if you check for 5 and 3, this is u and this is v, 3 and 5 is 8, right? So now the minimum between infinite and 8 is going to be 8. That is the minimum. That's why you give that value to the path flow. And then you basically say that parent tracker of v equal to v, which means that parent tracker of v, parent tracker of 5, which is 3, is equal to 3. So then that's why when you do the loop over again, the source, the sink value only changes, but you do the same thing over and over again. That's how you get the path. You go from here to here, you go from here to here, you go from here to here, and then you go from here to here. That's what happened. That's what's happening in this particular loop over here. Then you do the same thing. You do the same loop. See, we're doing the same loop, right? We're doing the same loop. But what's changing? What's changing is that even these lines are the same. See, even these lines are the same. Now you might be wondering why didn't just put these two lines in here, because I needed the path flow to be final. What is the path flow? The path flow is basically the smallest value in this entire range of the path. So if my path value is going to be 4 in this, my path value is going to be 12 in this, and so on and so forth. And then what I'm doing is I'm saying that the residual graph of uv minus equal to path flow. So I'm subtracting the path flow. So I'm subtracting 12 from this path. I'm subtracting 4 from this path. That's what we are doing. But also we are adding the path flow to the elements which are in the opposite direction. So if I'm going from here to here, but my path is from here to here, I'm adding the path, because if I'm going opposite to a single unidirectional path, I need to add the value. That's what I'm doing over here. Then you basically do the same thing which I just explained. Then at the end of the entire path, you basically say that max flow plus equal to path flow, which we did over here. See, max flow plus equal to path flow, max flow plus equal to path flow, and then we get the value of 23, which is returned. And that's how the entire code works. So yeah, I mean, I know this is a very difficult algorithm to comprehend, but I'm sure if you solve more problems like this, just watch the video again if you have any issues. And yeah, that's it. Thanks for watching, guys. Like, share, and subscribe if you enjoyed the video, and I'll see you later.